All right, so welcome back. So I'm going to conclude this lecture with a couple extensions, which I won't go over in any detail, and I'm not going to give a whole lot of insight into them, so I apologize for that. But just a couple quick results on the H2 norm and H2 optimal control, which are useful, and but I don't think there's any additional utility in going through the technical details of any of these. So I'm just going to basically give you the results and say, hey, this is there are a couple connections here, and make a couple comments on the utility of these things. So the first one is output feedback control. Right? So H2 optimal control, where we're doing output feedback. So we're looking for a full order controller, right? AK, BK, CK, DK, which solves the H2 optimal control problem, right? Which minimizes the H2 norm of the closed loop transfer function. Excuse me. Right. So fortunately, all that technical machinery we went over in lecture 10 also works for the H2 optimal control problem as well. And this reason is the structure of that LMI for H2 minimization has a lot in common with the structure for the H-infinity norm minimization. So in particular, right, if we apply that here, we sort of partition this matrix here, right? That was the AP plus PA block, right? And this was the C block. That was the B block, and here's the C block, and this is the X block, right? And if we apply the half-dual transformation to this system as well, we get more or less the same matrix terms as we had for the H-infinity control problem. So this is the same, right? If you remember from lecture 10, this is that same, right? What did I call it? XCL, right? Or actually YCL, sorry. CYCL. And this was the same XCLB that we had before. So the results essentially translate fairly directly, and we can use the same set of variable substitutions that we did for the H-infinity optimal control problem, which is quite useful because then it allows us to combine the H-infinity and H2 optimal control problems and sort of minimize both norms, or a weighted combination of both norms, with limitations, as we'll see. All right. So again, the control problem is minimize these half-dual variables. So this is the half-primal. This is the half-dual. Right. There's this matrix Z here, which is not the control variable. So in the LMI, it was W. It's positive. It's not the same variable substitution we had for state feedback. So don't get confused there. The A and B and C and DN, right, are the same transformed variables we had for H-infinity optimal control, and you can recover the controller in the same way from these A and B and C and DNs. Right, they lead in the same way to AK, BK, CK, and DK. There's a couple things to note, of course, right? So the LMI we had for ensuring that Y1 and X1 have a completion, an inverse completion of each other, right? That gets moved to this part of the matrix here. So instead of having Y1 I X1 positive by itself, right? It's in the 1-1 block of this LMI right here, right? So that gets moved over here. Other than that, let's see. Okay, the other thing we have is a constraint here, because remember, in the closed loop system, right, for the H2 norm to be finite, we need that feed-through term, direct feed-through term from exogenous inputs to Z, that D11 term, to be 0, right? So this enforces the D11 in closed loop is 0, right? So we have to add this additional constraint here to our problem. Otherwise, we might get, right, because we can choose Dn, we might get some non-zero feedback term, right? So that's a problem. And it's such a problem, actually, that you know, it's going to cause you problems if you try and do this in MATLAB. So the H2-Optimal control problem as an LMI is actually more reliable than the MATLAB functions that we sometimes get, right? So don't forget to include this. Otherwise, you're going to get a direct feed-through term, and you have infinite H2 norm, right? So we'll pose an issue there, right? But so then you solve the LMI, and you reconstruct your controller in the same way, right? Those are the variables from the LMI. We then construct our matrix completion in the same way. And remember, you could choose, I think the condition was x2y2 equals I minus xy or something like that. And then you could choose like y equals identity, and x2 is the remainder. Anyway, so you remember that variable transformation from the Hinfinity case, right? Hopefully. And then, so you use that to get AK2, BK2, CK2, and DK2. And then you use AK2, BK2, CK2, DK2 through this 1, 2, 3, 4 step conversion to get the actual controller, full state feedback controller, AK, BK, CK, and DK. Right. So because this is exactly the same variable substitution we used in the Hinfinity case, there's this very nice result which says that you can actually search for, right? And this is one of the benefits of using LMIs, right? You can just add additional LMI constraints to your optimization problem, and right, that will give you additional results. And so, in particular, since here's the this is the constraint that the closed loop system Hinfinity norm is less than gamma. We could add another constraint, another LMI constraint, which is this one. Right? So let's call this LMI1, LMI2. Right? So we had one constraint that ensures the Hinfinity norm of the closed loop system is less than gamma. And we had another constraint that says the H2 norm of the closed loop system is less than gamma. Different gammas, of course. There's gamma 1, this is gamma 1, and this is gamma 2. Right. So one constraint that ensures the Hinfinity norm is less than gamma 2, and one constraint that ensures the H2 norm is less than gamma 1. Right. And so when you're solving the optimization problem, right, you can do a minimization over all those variables that we talked about, right? The same, because x1 and y1, right, are the same for, they're the same half dual and half primal variables for both of these LMIs, right? They appear there. And we've got Z here, which is only for LMI1. We've got AN, BN, CN, DN, which represent the transformed version of the controller, right? In both cases, right? The closed loop norm of the system is the same in both cases, right? So these are the same. Right? So these AN, BN, CN, DNs yield the same K, right, in both cases. So this is an LMI, right, on this. Note, however, right, so there's two problems here, right? So the first problem is an easy one to understand. The first problem is that there's the gamma squared here. Remember, I talked about that. So it's not linear in gamma. Well, the solution, of course, as we talked about, is to make that beta, and then we have squared less than beta, right? So, okay, that's one thing. However, right, what are you minimizing, right, when you solve this LMI? Well, this is a true statement, right? It's a sufficient statement. It's not necessary. We'll talk about that in a second. So what are you minimizing, right? You can't minimize the H2 norm and the H infinity norm. So you can't do that directly. So what are you minimizing? Well, so one choice of your objective then is to minimize gamma 2 plus, say, 0.5 gamma 1, for example. All right. So you can minimize the H infinity norm, right? A bound on the H infinity norm. This is a bound. We'll talk about that in a second. And a bound on the H2 norm. So you can minimize both of those bounds, right? So either one. You can't minimize both at the same time. But you can minimize a weighted combination of the two, right? So you can minimize, say, your H infinity bound on the H infinity norm, plus, let's say, you give half a weight to the H2 norm, right? So you, so bound on the H2 bound, right? And in the end, of course, right, that guarantees you that the H2 norm will be less than gamma 2, and the H infinity norm will be less than gamma 2, and the H2 norm will be less than gamma 1. Well, actually, the square of the H2 norm is less than gamma 1. Well, if you could solve this, right? So let's actually do beta here. Ensures that, am I off the screen? Oh, sure, I am. So this ensures that the H infinity norm is less than gamma 1, and that the square of the H2 norm is less than beta 1, let's call it, or beta 2, what are we calling it? 1, 2, this is gamma 2, beta 1. Right, so, which isn't exactly optimal, right? Because, right, what we'd really like to do is, because, squares, they increase faster than linear functions, right? So it's not perfect, right? Because you're minimizing a bound on the H infinity norm, and you're minimizing the square root of a bound on the H2 norm, right? So for, say, large H2 norms, right, you're sort of minimizing the square root of that, and it doesn't really capture that, the fact that the H2 norm is increasing faster than beta 1, right? So you're really minimizing a bound on the H infinity norm, plus, let's say, a weight on the square of the square root of the H2 norm, right? So that's what your objective function actually is going to be doing. Now, is that good enough for you? Well, maybe, maybe not, but it's a limitation in any case, right? Not exactly what we want. So we can minimize something like this, right? This is our weight. So we can't exactly do mixed H2 H infinity optimal control, which is what we're trying to do, but if you do this, at least the H infinity norm and the H2 norm will be under control, right? They'll have reasonable values. So it's somewhat of a heuristic, right? but it gives decent results. But better than nothing, let's say. Right. So we can solve the H2 dynamic output feedback problem by itself. And we can solve the H infinity dynamic output feedback by itself. But when we sort of combine them by appending different LMIs, we have to sacrifice something. Because of the fact that the H2 norm, right, isn't bounded, because of this issue here, right, with the square, right. So, you know, if you could solve it, I know it seems like such a small issue, right? There's just one scalar with a square here, and it seems like it shouldn't be that much of a deal. And it's not that much of a deal practically, but it sort of breaks the LMI a little bit. So you get something that's a little bit more heuristic than we'd like. So anyway, this is what you're actually optimizing. So that's the first issue that makes this a little bit heuristic. The second issue is that the second issue is more important. The second issue is that, remember, these have to be the same variables, right? And these variables are related to AK, BK, CK, DK through two transformations. The first transformation to AK, BK, CK, and DK is not an issue. The second set of transformations, and I'll just go back to this slide here. The second set of transformations between AN, BN, CN, DN is related to these variables X and Y. Right? They're related to those things. So it's through those X and Y's that we get from AN, BN, CN, DN to AK2, BK2, CK2, and DK2. Right? So why is that a problem? It's a problem because the necessary and sufficient conditions, right, for this to be equal to the H2 norm and this to be equal to the H infinity norm, we're given in terms of x1 and y1. And remember what those represent. Those represent a Liapunov function. Just part of a Liapunov function, mind you, just that 1-1 block and the 1-1 block of the dual Liapunov function. Actually, I say and dual. And what do Liapunov functions, well, think back to Liapunov functions, right? Liapunov functions are a measure of sort of a system property, right? Every system property has its own Liapunov function. Here, let me just erase some things. So every Liapunov function represents a system property. So in specifically, there is a Liapunov function x1, let's call it y1, which represents the H infinity norm. And there's another Liapunov function, x2, x1, y1, let's put it hats, which represents the H2 norm of the system, right? And they're not the same, right? So the, just erase a few more things. So the LMI for the H2 norm, right, is given in terms of a Liapunov function, right, here, which is a necessary and sufficient condition. You search for that Liapunov function for the H2 norm. For the H infinity norm, right, a necessary and sufficient condition is given in terms of a different Liapunov function, x1, y1, given here. However, this LMI, we can't use different variables. We can't just say, right, this is x hat, y hat, right? and this is x, y. We can't use different variables for each LMI. Why not? So there must be the same x1, y1 for the H-infinity and the H2 LMI. And why is that? Because those variables are involved in the conversion of AN, BN, CN, DN to the closed loop, to the controller, right? X1, Y1 are involved in this conversion, right? And so we can't have different controllers for the H2 norm and for the H-infinity norm. We can't have a different controller, AN, BN, CN, DN, for each one. These have to be the same controllers, right? And hence, they have to be related back to AK, BK, CK, and DK through the same set of variables. Right? X1, Y1. So we can't use a different Liapunov function for the L and H-infinity LMI as we use for the H2 LMI. And so when we solve this problem, we're essentially looking for a Liapunov function which works to give us system properties for the H2 norm and gives us system properties for the H-infinity norm. And that is asking a lot of your Liapunov function. Okay? So this is a sufficient condition. This is a sufficient LMI for, so 2 implies 1, but 1 does not imply 2. Right? Because if we tried to, sorry, 1 does not imply 2. Because if we try to prove 1 implies 2, the KYP lemma and the H2 LMI are going to give us different x's. Different primal variables, which then of course lead to different x1s and y1s, which of course, right, yeah, lead to different different AN, BN, CN, DNs. Right, so that's a problem, right? That's so this is a sufficient condition. It's conservative, right? There may be a controller which achieves a better maybe a controller which achieves a better norm in this sense, even if you solve this LMI. Right. So this is conservative, a sufficient condition. Right. So, but it's the best we can do, right? If you can solve this problem exactly, great. But I have doubts that anyone is going to be able to solve this problem exactly in the near future. But so anyway, so that's why, again, I don't emphasize it quite as much as the other results, because it's not exact, right? It's a sufficient condition, but it's a sufficient condition which is better than the alternative, which is nothing, right? Right. So anyway, if you solve this, right, you apply the variable inverse, and you're going to get a controller, and it's going to work okay, maybe, but we don't really have a bound on how well it's going to work, or it could be very suboptimal, it could be only a little bit suboptimal, it could be exact, who knows, but we just don't know. Right. So I give it to you, it is what it is, people use it a lot, I think, but it's not perfect. Right, so finally, let's conclude this lecture with a couple more connections. So we'll first connect to the Kalman filter in continuous time, then we'll connect to the Kalman filter in discrete time. Because why? I don't know. Because most people are familiar with the Kalman filter, so they'd like to know what is the relationship. We talked about the relationship to noise. We talked about the relationship to LQR. So here's another relationship. This is also defined by noise, however. So a lot of the sort of real fundamental results, things you can actually prove for the H2 norm, come back to noise. So let's deal with the Kalman filter. So the Kalman filtering problem, right? Right, here's our nominal system. So there's a nominal system. It is corrupted by noise, so this process noise. Right? It has an input, although the Kalman filter doesn't require an input. Right. So it has an input. It has white noise. It's an unfiltered white noise, so we're going to assume it's unfiltered. There's no B matrix here. Unfiltered noise, although it doesn't have to be white noise, right? So in particular, we can, if we have we can have the spectral density of the noise given by a matrix V. Right? So that's process noise. We have an output, so measurements, sensed outputs. Y, which are a function of the state, and they're also corrupted by noise. This is sensor noise now. Right. So that's the system we're observing. Right. The Kalman filter is an observer, I should say. So what is the Kalman filter? It looks a lot like the Leuenberger observer, right? It has the same structure as Leuenberger observer. Right, which we went over in lecture 6, I believe. So basically, we have a estimated state. Which has the same dynamics as the plant, right? AX. The input affects it the same way, assuming we have an input. And there's a correction factor. So we propagate the state the same way that the plant propagates the state. And then we have a correction factor, which is the difference between the output we actually observed, the sensed output, and the expected output. Right? So what's the expected output? Right? The expected output is just the Cx hat term. Right? Right. And then, so this term then is the surprise. Right. It's the difference between what you expected it to be and what it actually is. Notice that our expected output does not have noise because, of course, we can't actually measure what noise is corrupted. We can't measure the sensor noise, obviously. It doesn't make any sense. So obviously not measured. Right. Right, as with the Leuenberger observer, we form the error dynamics. So the error dynamics. Right, and so the error, of course, remember, is the difference between the, I don't think it say it here actually. Error is the difference between the predicted state and the actual state. Right? And if you close the loop on these dynamics, right, what do you get? Right, you get this dynamics here. So same as we saw for the Leuenberger observer, A plus LC, but now we have exogenous inputs. So this is the same. And this is different than we saw earlier. New terms. How the exogenous input affects these terms. So obviously the process noise, right, it directly affects this error, drives that error. And the sensor noise also drives the error, but filtered through our gain, right? So we can't make our gain too high, or that sensor noise is really going to, we can't trust our sensors too much, or that sensor noise is really going to upset our error dynamics. Right. So you have to be careful about your L. And this is the difference between optimal control and just state feedback, right? Pole placement, for example, is that if you have big sensor noise, right, you have to be careful about your L. Right? So hopefully we've measured these noises to some extent, right? So this is our power spectral density, the variance of our process noise. And now we also have a measurement of this power spectral density of our sensor noise. Right. So we've measured both of those things, right? The Kalman filter is a H2-Optimal controller. State feedback, essentially. It's not actually state feedback because it's a dual of that, right? It's the estimator, which we haven't actually gone over. We haven't solved that problem yet. But the H2 optimal estimator is just the dual of the H2 optimal controller, so we could solve that problem, but we didn't, right? So it assumes we know something about our noises, this power spectral density of our noises. And if we do, and here it's given in terms of actually a Riccati equation, right? Not an LMI. And I know it's an LMI course and I'm giving our Riccati equation because I actually don't want to spend too much time on it. You can solve this differently, right? You can solve this by solving the dual to LQR problem, right? This is an LMI solution. But because I want to give the whole thing on one slide, I just give the Riccati equation solution without getting into it too much. All right. So you solve the Riccati equation. Your weights on these noises, pre-filtering if you like, show up here, right? These are the noise power spectral densities. The number 2, of course, is the sensor noise. Number 1 is the PSD of the process noise. Right. Here, C is just your C matrix. A is just your dynamics. Notice that B doesn't show up here. Right. As I said, right, B is optional, not required. Right. Doesn't affect the problem per se. Right. So the Kalman filtering problem, the Riccati equation, says if you solve that equation for sigma, so sigma is in a way our Liapunov function, right? In a way. Right. If you solve for that Liapunov function sigma, and you design your gain to be equal to this, which is similar but not exactly equal to that KP inverse, but not exactly actually entirely. So you set your gain equal to be this this gain. Then the effect of the noise on the variance of the effect of the noise on the variance of the error is minimized, right? So minimizes the power spectral density of the error. Error signal. Right. Whether that's something you want to minimize or not, but that's what the Kalman filter does. Of of course, because you've chosen your Kalman filter to have the Leuenberger observer structure, that implies the separation principle holds. Which means that if A plus LC is stable, which it must be if this is to be finite, right? Although you have to be careful about that because remember we're doing H2, so we don't necessarily have a guarantee, right, that this is stable. Right. But if you do, right, if you have that guarantee, and I believe the Kalman filter is guaranteed to be stable, A plus LC is guaranteed to be stable, then if you ensure that A plus BK is also stable, right, 1, 2, the separation principle shows that the closed loop system is also stable. Properties of that closed loop system are non-existent. The only thing you're really guaranteed is this. Right? Again, what we talked about in part A, that we are minimizing the power spectral density of an output. In this case, our output is error. Right? Different color. Right. So that's the only guarantee we have. Other than if this is stable and this is stable, we have closed loop stability. In any case, right, it also reduces to the LQR problem. It's often called the LQG problem, where now we've replaced these weighting matrices with these variances, power spectral densities. Of course, right, in any dual, right, we replace K with L transpose, we replace A with A transpose, B with C transpose in the LQR problem. And so we could solve this with an LMI. Again, I don't think there's no homework assignment on it, but we wanted to make that connection. Finally, just to be complete, I also give a result for the discrete time Kalman filter, which is very similar to the continuous time Kalman filter. I also give it in terms of a Riccati equation instead of an LMI. In any case, so the connection here is very tenuous to LMIs because I didn't give an LMI for optimal state feedback or optimal observer feedback in the discrete time case. We didn't cover optimal control in discrete time. Maybe you wanna do a project on that. Be great to add that to our website for the wiki book. In any case, let's get started. It's really, I don't want to spend too much time on it, but here it is. Here's our system, nominal system, process noise. Here's the sensors, sensed output, sensor noise, same as before. Estimator, as before, right? Propagate the estimator, propagate the estimate. Surprise, right? This is the expected output, y hat, minus the actual output, surprise term here. And we have a correction term which gives a weight on the propagation versus the surprise correction, right? So you have a gain term here. Again, this is a discrete time now, but we can also form these covariance matrix, these power spectral densities in discrete time now. Where's W? Yeah, there's W. There's a process noise, sensor noise. Right. Process that right here, sensor right here. So the error dynamics, right, are thus. Actually, I'm missing some terms here, right? There should be some errors here, right? This is WK plus LVK. It should be something like that, yeah. Sorry, forgot about those. So there's the aerodynamics. Again, Kalman filter, right? We solve a Riccati equation to give us zeta, or epsilon, which is sort of a Liapunov function, right? We then construct our observer gains based on that Liapunov function, right here. Notice that there's an A term here, right? Which is different than in continuous time. And what have we got here, right? So we've got a gain, we've got a Riccati equation, and the result is to minimize the power spectral density of the error again. Again, here we don't have, I just, because, right, it seems unnecessary, I didn't put the input here. Right, no input, right? So this is just open loop estimation of a dynamical system, right? Of course, you could add the controller, right? If you like, but I haven't done so here. Right? And there's a stability, right, of A plus LC, right? So it turns out actually if a sufficient condition for this A plus LC to be stable is if these matrix pairs are observable and controllable. So basically, if A coupled with the process noise and C and CA is observable, then the closed loop is stable. Right. So again, right, there is a dual formulation to discrete time LQR, but I feel kind of guilty even giving this. I just wanted to talk about it because, right, everyone knows what it is. But I feel guilty because we haven't actually covered discrete time LQR in any sense, much less estimation, optimal estimation. But I just, give it as a little bonus, right? So again, we don't give it in an LMI, but there are LMIs which can solve this, and it would be great. There exist LMIs. It'd be great if someone could add them to Wikibook or something like that. Maybe we'll add them to the lecture at some point. Although, again, I don't want to make this lecture overly long. So there exist LMIs, but I don't give. So again, right, this is just adds interpretation to the H2-Optimal control problem. Right, the H2-Optimal control problem is to minimize the effect of sensor noise. To minimize the effect of noise on the system. It could be sensor noise or process noise. It has a connection to LQR. Right, this also solves the LQR problem. So the optimal control, H2-Optimal control, gives you LQR, gives you LQG, gives you Kalman filter, gives discrete Kalman filter. Works in all of these cases. I don't go over it in too much depth because I don't really like the H2 norm, but also just because to avoid getting bogged down. And anyway, on that somewhat unsatisfactory and sort of anticlimactic note, we end our lectures on optimal control. We conclude our lectures on optimal control. These are lectures 7 through 11. Right? basically, we've solved a great number of problems. We haven't solved every problem. In this case, we've just indicated, right, a solution. We didn't go through the solution, but we've solved the biggest problem, which is H-infinity dynamic output feedback problem. Connected it to several other problems. Solved the H2-Optimal control problem. Introduced the coupled, or the combined H-infinity optimal control problem, and then motivated the H2 norm in certain circumstances. When we come back in lectures 12 through, I believe, 15, we'll consider robust control. And robust control is a natural extension of the H-infinity framework. We'll see that there's a strong relationship between optimal control and robust control in terms of the LFT, in terms of minimizing H-infinity norms and guaranteeing closed-loop stability and things like that. But that will wait for future lectures and future discussions. So at this point, I will end this section of the course and wish you luck in your optimal control problems.